Good afternoon to all, and welcome to the MathWorks Wireless webinar series. I'm Prashant, part of the marketing team at MathWorks, and will be your host for today. The wireless series was a uh, sorry about it. The wireless series was spread across 3 days, covering some of the most critical and interesting areas of wireless technology. The first two sessions were covered yesterday, and the recording for the same will be shared in the coming few days. Before we start, there are a few points to consider. You can join the audio by clicking the call using computer option and ensure your speakers are not muted. In case of any issues, please feel free to contact the host using the chat function. Here's the agenda for day 3, and we have an interesting lineup of speakers taking you through the session. The session is for 60 minutes, and in the interest of time, we'll have the Q&A session towards the end. However, if you have any question, please post it in the Q&A section. And at any given point of time, our host will keep a tab of it and will have it answered for you. We'll also have the polls during the session, which will pop up on the right side of your screen. So here are our speakers for today. Our first speaker is Mr. Vinod Thiruvas. He's currently working as the Senior Technical Lead at Capgemini, focusing on complete FPGA-based RRH design for 4G LTE and ORU5G NR systems. He has more than 15 years of industrial experience in the field of signal processing, wireless and optical communication system design, assuming various roles in companies like Samir, HCL Technologies, Tesla Semiconductors, and Capgemini. Our second speaker is Niharika Agrawal. She is an application engineer at MathWorks, and her main area of research is the waveform design for air-to-ground communication, hardware implementation of end-to-end transceiver architecture using HDL and embedded coder on FPGA. I would now like to hand it over to Vinod, and I will meet you during the end of the session. Thank you.
Okay, thank you, Prashant. Thank you. So this is Vinod. I'm working as a senior technical lead in Capgemini. Here we are going to. I would like to share our experience, what we had with MathWorks in the part of our complete ORU design based on 5GNR.
Vinod, I'm sorry to interrupt you. Can you just hide the presenter's view? Then we can see the full screen. Thank you.
Okay, sorry. Yeah, sure. Is it okay now? Hello?
Better.
Sure. Okay, so here we are basically working for UE emulator, the radio unit based on UE emulator. So in this activities, we were mainly focusing only on the radio part of the UE side. So this UE emulator will be sitting in terms of it's similar to our like TM500 equipment, where the radio part of the unit has been given to us for our as a project for Capgemini. In this activities, maybe I'll just go to the next slide for our this presentation. I would like to take it up our what is the agenda of this session. Maybe like first I'll be giving a brief introduction about 5GNR system. and what will be the features supported in our U emulator, this FPGA, and we'll be going through the detailed architecture of our FPGA, what we have designed for, and design and implementation strategy, what it was taken into, and how MathWorks is getting used into our basic design flow. Then we'll go for our benefits of MATLAB, and we'll go for the conclusion session. Let's see a 5GNR system overview. Maybe you guys have been seeing these slides in a quite longer time for since 5G is evolving thing. It will be talking from all over the world about this 5G system. So it can be this 5G systems is mainly focusing on three parameters, like three features. Majorly, I'll just talk about three major features or use cases: enhanced mobile broadband EMBB system, and ultra reliable low latency systems URLC, and massive machine type communication. Machine type communication will be having more advantages, like in IoT based communications and in artificial intelligence. So all those things we are having the worldwide across worldwide, we'll be using all these systems. So in our Capgemini, what we have done, we have taken the project for designing a radio system, like which is compliant to ORAN for an UE emulator. So basically, we see that NR systems has two major units, like a G0 B system as well as our UE emulator. So we are focusing only in this area. Our major focus is based on this radio part. So in GNB systems, we'll be having radio unit, distributed unit, and central unit. In radio unit, we'll be having the lo-fi and all the RF related activities, like digital front-end processing, and the interface towards the RFICs will be sitting inside the FPGA. It can be either FPGA based or an ASIC based solution. Now the ASICs is also evolving for a small cell based application for radio unit. And let's talk something about distributed unit, where we'll be focusing on Hi-Fi, Mac, and RLC based applications running in the Hi-Fi, running in the DU system. Between Hi-Fi and Lo-Fi, we'll be having a dedicated frontal interface called eSPRI and ORAN, Open RAN, where we are working for 7.2 split based ORAN systems. And if you see something about central unit, it will be handling of the PDCP parameters. Now the GNB will be communicating to validate this GNB. We need some user equipment. So we are trying to develop this user equipment as an UE emulator, where our RU functionalities has been taken as an activity from Capgemini side, and our focus is mainly on RU side. So in this GNB, we RU systems, RU side GNB will be like will be doing the downlink transmission, and this transmission signals will be coming through an antenna, and UV will be receiving these signals from the RF side. Then next lo-fi implementation will be done inside this RU, and which will backend pass this data towards DU in UV emulator. So UV emulator, we have segregated three basic units, like ORU, ODU, and OCU, similar to our GNB system. In this ORU in UV emulator, we have done the major functionalities, two major functionalities, which will be an reverse way of doing it in ORU in GNB. Like downlink transmission in GNB will be like our downlink reception in ORU in UE. Similar way, uplink reception in GNB will be our uplink transmit signals what we are going to give it to our ODU in UM later. So here we'll be talking about, we'll be doing the functionalities like uplink, downlink signals we'll be receiving here, and uplink signals will be transmitting from this radio unit. So the whatever the signal that we are receiving from this antenna will be the downlink signals. We'll be doing all the low-fi functionalities and passing this signals to the hi-fi for other hi-fi processing, L1 and L2, L3 processing as well. Similarly, the L2, L3 processing data will be coming on the transmit side, meaning like the downlink side will be getting uplink side will be getting transmitted from here, and it will be getting passed towards the antenna to this GNB. So this is the major change people will be doing mostly on the GNB based RU design. In our Capgemini, we have done this on the UE emulator side. Next slide, like our UE emulator RU design will be supporting either 10 gig or 25 gig Ethernet interface compliant to ORAN 7.2 split towards the ODU in UE emulator. And we may need to do the lo-fi implementation as well, which includes that IFFT, FFT, and other processing on both downlink and uplink chains. Similarly, we have asked to do the part of the initial cell search procedure processing, which will be planned to do it in ODU in UE emulator. But now, to reduce the complexity of this ODU, our customer asked us to take it this SSB processing in the ORU side. So this is the major change which will be doing inside our UE emulator in the ORU side. So other digital front-end processing we have done, and also we have implemented some of the RF impairment logic. So these are all the major features that will be supported in the RU side, UE emulator. So if we come to the FPGA architecture, so here in this UE side, we'll be having ODU and ORU. This side will be the left side towards this will be our ODU, and right side towards our GNB. So we'll be receiving the signal from this GNB, and we'll be receiving the signals on this side on the ODU side. So here we are having 4 parallel interface towards 10 gig interface towards ODU, and 4 parallel interface towards JST side. So we are having this FPGA based on the Intel FPGA, and this is interacting with RFIC towards JSG 204B interface. So this complete unit is given as a complete unit to us, where we are having the ORU unit, which consists of Intel FPGAs and external RFICs from third-party interfaces. So this ORU we are supporting for all the NR bandwidth starting from 5 megahertz to 100 megahertz, and with the subcarrier spacing of 30 kilohertz. We are supporting it for FR1. We have designed it for FR1 frequencies. So in this architecture, we have taken down on this side, we'll be having the uplink transmission signal from ODU to GNB, and downlink reception signal from G node B to ODU here. In this processing, uplink side, we'll be having normal FFT and CP insertion processing for the uplink, all the uplink channels. We are having separate PRAT channel as well. So PRAT signals and normal PUXCH and PUCCH signals will be coming from the ORAN interface. We are doing that separate FFT processing and CP insertion processing for both PRAT and PUXCH. Then we are combining it, those two channels data, and we are passing it to the DUC where our upsampling has been done to, with the rates matching to the external RFIC. This is on the uplink transmission path. Similarly, on the receiving path, we'll be down converting these signals, whichever the signals received according to the sampling rate of 122.88 megahertz sampling, megasamples per second for 100 megahertz bandwidth, 30 kilohertz space subcarrier spacing. And we have done the RF impairment logics, like we have implemented RF impairment logics like DC offset compensation and correction. And similarly, we have implemented IQ gain and phase imbalance and corrections. Later, this signals can be directly given to the SSB processing. We have taken this SSB processing like signal synchronization, SS burst processing. So SSB, in short, we call it as SSB processing. SSB processing will be having like three major blocks inside this SSB processing, like one is PSS, SSS, and PBCH signals. So PSS, SSS is mainly used for our initial cell search access process, as well as our PBCH complete processing has been implemented inside this FPGA for all the for one of the four channels, because since this PSS SSB processing load will be getting high inside this ORU, we have done this implementation, SSB implementation for only one channel. Since we are having four channels on this side, this RU unit supports 4x4 MIMO. So 4T4 are base solution. So we are doing SSB processing for any one of the four channels received inside this downlink chain. After post processing of this signal, we'll be giving this offset like MIB bits has been recovered, and which will be used to know the frequent start of the frame. Based on this start of the frame, we are passing this samples to the IFFT, and CP has been removed based on this symbol tick. Then after IFFT processing, this signals has been transmitted towards the eCPRI and to ODU side. So these are all the major activities that has been implemented in our ORU FPGA. So major blocks that has been implemented like SSB processing in MATLAB. Similarly, we have implemented IQ gain and phase imbalance. Similarly, of our DC offset implementation, digital up conversion, down conversion for all the four channels has been implemented using MATLAB. So here, these are all the major activities in this design. Our implementation strategy, like we are having this frontal IP integration and eCPRI overhand towards frontal side, and SS bus processing like what I discussed from the previous slide. So it is an expanded view of this. Maybe you can see this example design. We have taken this example design from wireless HTL toolbox provided by MathWorks, and we have modified this example design according to our custom requirement. So we have done this IP, we have taken this example reference design from MathWorks. Then this IP has been modified for each of these parameters for each side, like PSS, SSS, and similarly our PBCH. So these parameters, so PBCH demodulation, we have taken like our polar decoding has been implemented inside this PBCH demodulation. So we have our customer were interested to use their PVCH demodulation for this their polar decoding IP, and it has to be integrated in this chain. So this was the ask from the customer, and anyway we have taken third party PVCH third party polar decoder IP in this PVCH processing, and using our wireless HDL toolbox. Wireless HDL toolbox provides polar decoder IP which is compliant to 3GPP. So we have taken that as the reference, and we have compared this third party IP code, and we have compared these two results whether it is matching fine or not from the polar decoding IP point of view. So later all these this code is directly converted into a RTL using our HDL coder, MathWorks provided HDL coder, and we have integrated this into our custom logic design. So the complete part of this design has been integrated and in both uplink and downlink chain from Capgemini, and we have validated this design using our standalone modules for each module level simulation, and all these module level simulation test vectors has been taken in 5G toolbox, so with the waveform generated using the 5G toolbox, and each modules has been validated or verified individually inside this MATLAB chain. So coming to this tools, whatever the tools we have, MathWorks has rich varieties of tools supporting our applications like MATLAB, Simulink, Communication Toolbox, Signal Processing Toolbox, 5G Toolbox, and Wireless HDL Toolbox. So we have converted this HDL toolbox using this fixed point designer. So we have taken all the bit level accuracies has been considered while designing this design process, which will be increasing this resource utilization from the FPGA point of view. So pros and cons has been considered using all these toolboxes like to specify the IQ bit width. So majorly to specify the IQ bit width, there we have facing some challenges for each and every stages of this design. So that has been successfully simulated using these toolboxes, and our design has been taken into a consideration of like which verifies our bit level accuracy against all the IQ samples for all the downlink and uplink channels has been verified against these toolboxes. And MathWorks helps a lot in our design process where we have taken this ORAN development as a first step from the UV emulator point of view. So MathWorks helped a lot in this design activity, and with this shipping example design like NRHDL, cell search, and MIB recovery model. So this recovery model has been taken as an example as a starting point where we have integrated our other rest of the logics using uh, uh, our RTL design flow, normal RTL design flow. So we have obtained the results like we have considered like our development time has been completely reduced by 50% using this self-search process implementation. So we have considered a good amount of time for SSB implementation. Then from the rest of the logics, like we have considered some duration with the schedule. So we with this MathWorks product using wireless HDL toolbox, our development time has been completely reduced by 50%. So that we told that at least these products have been variety used to have this model-based design framework works a lot to cut down our development time, and we can easily deliver our solution less than a year. So synchronization of the subsystem that has been achieved earlier than what we have expected. Meaning like we used our customized hardware from our customer, but we were able to confirm the frequency offset synchronization between our ODU, ORU and the GNB after some couple of experiment trials, which we were anticipated some couple of weeks back to make this synchronization happen between this ODU and ORU. But some of the trials has been easily taken to a next stage for our while integrating this UE with our GNB system. Then coming back to the next point, last point, like system implementation validated on the very first attempt, like our design and implementation of our MIB recovery model running in the customer hardware, which gives the frequency offset like MIB bits has been recovered, and this initial cell search process has been successfully transferred from UE emulator to GNB. In our very first attempt, it has been validated against the GNB system. So that's it from our side. Like what are all the major activities from Capgemini, what we have done using along with the MathWorks toolbox. So thank you for your presentation. This is the last slide that I am having from my side. I'm done with this presentation. Thank you.
Thank you, Vinod, for this insightful presentation. Dear audience, if you have any questions, you can put it in the Q&A section, and Vinod will be kind enough to answer it.
Vinod, we have one question here. Question is, can you elaborate on why the SSB processing has been pulled into the ORU instead of being kept within the ODU unit? Could you answer that?
Yeah. So ODU, yeah, yes, it will be normally you implementing all these processing like downlink process, complete downlink process will be done inside this ODU. But to reduce the complexity of this ODU, maybe like our customer was interested to take all the initial cell search processing into ORU. So this is the requirement that we got from our customers.
Thank you, Vinod. We'll wait for a couple of more minutes just to see if there are any other further questions. If you have any questions for Vinod, please put it in the Q&A panel. Vinod, there is one more question. Can you provide more details on how you verified the integration of custom polar decoding IP into the reference SSB processing implementation using MATLAB and Fuzzy Toolbox?
Yeah, so we got an IP from, it's like a third-party IP polar decoder. We got it as the reference model as well from the simulation side. So our customer has not that IP. They have the example design, but the example design doesn't provide the test vectors to us. So which will be we have taken then wireless HTL toolbox. Wireless HTL toolbox also has polar decoder IP compliant to our 3GPP specifications. So we have generated 5G NR waveforms using 5G toolbox, and we have injected these signals to both the polar decoder IP, and we have verified this their both of these IPs performance. Just like a bus function model has been considered like our MathWorks polar decoder, and we have verified our custom third-party IP design. And the end-to-end flow, yes, we have some results obtained based on our third-party. So based on the third-party IP design, we have taken our MATLAB polar decoder as the reference. That's the main key item that I would like to highlight it here.
Yeah, thanks, Vinod, for answering that question. So I think in the interest of time, we can now move to the next presentation. So over to you, Prashant.
Thank you, Tabriz. Our next speaker will be Niharika Agarwal. Over to you.
Hello, can you hear me? And my slides are up?
Yes.
Okay. Okay. Hello, everyone. Welcome to the webinar session on prototyping and verifying wireless systems on FPGAs and ASICs. So we know that RTL verification is a big challenge in FPGA and ASIC design. In this webinar, we will look out some ways to improve the verification by connecting it to MATLAB. So, okay. So we will start with analyzing the root cause of these issues, and that's where the communication gaps between the different roles comes into the picture. Then we'll see how our MATLAB can help to cover up some of these challenges, and finally we'll see that how some of our customers are using MATLAB to do more verification earlier in the process. So the first important question arises is why the verification is very important. So while you do the ASIC design, once you tape out the chip and send it to the fabrication, at that time you don't want to find any bug, because that will cause you a lot of respin and which will cost you, which will be very expensive for you and a lot of time taking. So when we see the survey conducted by Mentor Graphics, the statistics shows that the 75% of ASIC projects require silicon respin, and there can be multiple causes, but the leading cause for the 41% of R is still functional flaws. So if you think that this won't occur in case of FPGA because it is reprogrammable, but what if that FPGA is an aircraft or space or satellite, and where you can't reprogram the FPGA, and or it is in the assembly part where you don't want to switch off that? So then you would definitely not want to escape those bugs into production. So according to this survey, still the 84% of the projects have non-trivial bugs which escape into the production, and in which 48% of the 48% of the bugs are still logical because of the logical or functional flaw. So typically, what is happening is the industries are using the conventional workflow, where different teams are divided to do a dedicated work and communicate only via manually written and read specifications. So the design team manually writes VHDL or Verilog code. The verification team then creates a test bench environment like verification architectures, stimulus, golden reference models to ensure that the design meets the specifications defined by the design team. So all this process is done manually, and usually they spend all the time verifying, and at the end they found that the design doesn't work in the system context. So this requires a lot of time and a long iteration to fix it. So the so this is how, like, the biggest root cause is basically, we can say, the communication gap of the details. So what is happening here is that system or algorithm designer will typically use MATLAB to design the algorithm. They capture how it is supposed to work with the specification document, and then they throw those specifications over the wall to the hardware design, and hardware design team use to figure out that how we can implement it and verify it. So from the survey in the previous slide, we can see that the biggest percentage is from the specification flaws. So we can say that these two categories create the root cause of these issues. So these two categories mainly are the changes to specification. Whenever there are specification changes, then you need to do all the specification captures, design the design, implement it on the hardware again and again, and also the incorrect or incomplete specification part. So we can reduce and we can address these issues and improve the verification flow by connecting it to the MATLAB. So our product, the HDL verifier, brings together the system context and hardware design. HDL co-simulation simulates the design in the HDL simulator connected to a system level test environment in MATLAB or Simulink. And FPGA in the loop does the same, except that the design is loaded onto actual hardware. So in HDL co-simulation, we don't deploy it to the hardware, we do the pre-verification. And in FPGA in loop, it's the design is loaded to the actual hardware for high fidelity and high speed simulations. And then we generate the system Verilog DPI component generation, which exports the golden reference models, stimulus system models, and anything which is code generatable from MATLAB or Simulink, which speed up the verification environment creation. So basically, these are some workflows which helps to improve the verification efficiency as well as reduce the time consumption. So now let's see how our MATLAB workflow will help in generating the system Verilog DPI component and integrate it with the universal verification method UVM. So we know that a lot of effort goes into the designing and testing the algorithms in MATLAB, right? When it comes to implement the algorithm on a hardware, specifications must be written to describe the behavior and handed over to the hardware design and verification engineers. So in FPGA and ASIC verifications, roughly 20% of the verification effort is spent in the only in the test bench creation, and this involves writing tests as well as the creating verification models. So once the verification, so the verification team then typically creates a UVM environment, and they have to create the test plan for sequences. So sequence checker they have to create, and a self-checking scoreboard contains a self-checking scoreboard they have to create, which contains the golden reference model on based on that specifications, so that they can use that golden reference model to compare it with your with the design part, with the algorithm. So but the main question arises is why always have to recreate once the specifications are changed, even when we can reuse them. So for that, we have this HTL verifier product where we can generate system Verilog DPI component directly from MATLAB functions. So it basically relies on the MATLAB coder to generate C code that captures the functionality and wraps it up in the DPI interface, so it can be plug-in ready to any system Verilog environment, and which compiles and build a DPI library if the simulation is running in the same environment, means MATLAB environment. So the system Verilog DPI then interface then can easily import those C codes into verification environment. And so what it does, it bypasses the need to capture the algorithm behavior as a specification, and everything here becomes automated. So it works as an executable specification which can be used, for example, as a golden reference to the scoreboard. So in this case, if it allows you to reuse many different items such as like golden reference models, stimulus, external environment models, all these things you can reuse it instead of recreating again and again while specifications are changing. So there's also an export for DPI as well, where you can have the C side calling the system Verilog file, system Verilog, and but we don't do anything in that space. So because one challenge with this DPI is that there is no notion of time. So if we generate a model that consumes time, say waveform stimulus, then the sample rate has to be contained in the DPI component. And also we use MATLAB coder or Simulink coder to generate the component in which the appropriate C code generation will be there and following the appropriate guidelines. So here I'll just show a overview of an example where how we can reuse the communication algorithm engineers developed to generate a 5G new radio waveform for system Verilog verification. So basically here this 5G and LTE or WN toolbox we have as a wireless HTL toolbox as well, where we can add the hardware architectures and sample processing and timing notions in the early stages. We can also do the fixed point conversion using fixed point conversion toolbox, which is also the automated toolbox to convert the floating point design to the fixed point design. And this example basically show that how we can use a standalone test bench with DPI component to validate the SSB decoding module of an MIB recovery process. So the HTL verifier generate the DPI component which supports tunable parameters, and it also enable customization to the 5G waveform from the top level test bench. So what basically at the backend HDL verifier does is it calls the MATLAB coder to generate C code and builds everything to link it into a system Verilog simulation. So basically it will run in the system Verilog simulator. So the video of this simulation, the example explaining, can be found in the link in the slide, which we'll share later. And so with this HDL verifier, we have a good user story. We worked with NXP Semiconductors to support them in verification of a complex mixed signal design, which was having a lot of digital signal processing elements and multiple modes of operation. So the main challenge with the verification of that design was to verify it sample by sample, which when we verify it sample by sample, it requires changes to UVM components whenever the design is changing. So the solution which we came up with a solution of writing SNR and PSD functions in MATLAB and generate system Verilog DPI component for the UVM part. So this helped them to reduce the verification time and improve the verification at higher level of abstraction by enabling the analysis with regressive test runs. So then the system Verilog DPI, this import declarations are automatically generated in .sv files, system Verilog files, and these files can be compiled with the design as well. When we do the system Verilog UVM integration, we put the wave generation DPI component into the test sequence, and we put the checker or the result testing in the scoreboard part to analyze the results basically. So with this, what happens is, rather than using a manually written specification document as a primary source of communication, this HDL verify capability basically allows for direct generation of the models, and this eliminates a lot of manual work from the upfront part of verification process and reduces issues over specification misinterpretation. So it also accommodates the specification changes much more efficiently, because it is an automated process and you implement and verify any changes at the algorithm level. So basically you don't need to change at the later stages and regenerate the model. So after seeing the system Verilog DPI component generation, we will see that how MATLAB will help in debugging it with the co-simulation as well. So there's another method for verification is co-simulation. So what if we found a mismatch? So when you need to debug with visibility into both test bench components and the DTU, the DUT, the design and test RTL. So we offer the ability to co-simulate. So here it co-simulates with the third-party HTL simulator, such as like the simulator from Mentor and Cadence. And the DUT RTL can be handwritten or generated by HTL coder. Both the things are set up automated. So HTL coder basically generates the error-free synthesized code for your design. And HTL verifier can also take this co-simulation can also take a pre-handwritten HDL code and import that into Simulink, or it can use the code generated from the HTL coder as well. And most of our customers use Simulink to co-simulate because of its built-in notion of time. So Simulink basically communicates the current simulation time to HDL simulator at each intermediate step. And to bring the HDL simulator up to date with Simulink during co-simulation, uh, first you have to convert sampled Simulink time to HDL simulator time. So what it does is, and it allows HDL simulator to run the computed number of tricks. So when you allow the software to define the timing relationship, what it does, it will set the timing relationship close to as one sample time in Simulink will be equal to one clock period in HDL. And if this setting is not possible for your design, then then HDL verifier attempts to set the signal rate on the Simulink model port of the lowest possible number of HDL simulator ticks for timing calculation, basically. So this enables the different roles to coordinate together in one single environment. And once we have that, then we can see that how we can start verifying earlier. Okay, so first we can make our design. First, the thing is that all the design and models and algorithm, the test cases, everything is in the same test environment. So we can make our design more robust by taking the initial frame-based algorithm to refine it with more implementation details. So you can add streaming behavior. You can convert a fixed floating point model to fixed point. Again, I have told you with the fixed point design, automated fixed point designer tool, and finally, you can add the hardware architectures to see that how it will actually operate in the hardware. So all these things we can do it in the MATLAB environment. And at any level of these models, you can generate DPIC components. So you can have different levels of information or details in your DPI, which you can export out for the verification. So once you have all roles collaborating with different versions of these models, then you can test them with different verification methods built into the Simulink model. So you can take these different models and create test sequences or assessments to verify model. You can test harness to isolate a subsystem, or you can also track coverage at the model level, in which you can look the conditions ranges or the executions. It also checks the signal ranges, and it accumulates data for the multiple runs. And but we have the coverage at a model level. We don't have the coverage at the bit level as much as we have it for the model level. So you can still test your bit level or RTL as the RTL verification. And we have the assertions within the design itself, which can be your static check, runtime check, providing properties. So it will also check to see the ranges. It will also check the algebraic loops, like those should not have, suppose 0 by 0 in your design or in your algorithm. So any algebraic loop it will check. And then for the requirement side also, we have the access coverage to like link requirements to model and test and generate code as well. So now our customers say that if I'm doing idly verification and I'm doing the fixed point conversion as well, then why will I do the handwritten HTL coding? That's true. And why should he get a chance to of errors while handwriting? So that's true. So we have the ability to do the automatically generating code by HDL coder, and this HDL coder basically generates an error-free synthesizable RTL code for your design, and you have full control over optimization. So basically, you can control the resource optimizations. You can control the speed optimization using pipelining. You can share the resources there. You can so basically full control over the optimizations are there. The codes which are generated from HTL coder are readable and traceable. So what I mean by traceable? You have the bidirectional traceability in the HTL coder. Once you generate the code, you can click on the any code module, HTL or Verilog code module, to check that which this module is representing which block. And you can click on the block and check that this block is representing which module of the HTL generated HTL code. So these HTL codes are fully synthesizable, and you can even generate the bit stream like at the it will use the Vivado at the back end, and it will generate the bit stream for you, which you can directly dump on the hardware side. And we support a lot of hardware boards, evaluation boards. Also for any custom board, we have a different workflow for custom board code generation as well. So one of our leading customer, Nokia, speeds up their prototyping using the HTL coder in their project. Earlier, they were looking to be able to get onto an FPGA prototype sooner. So their existing workflow required them to write the write the RTL, write the test bench, and then verify the RTL. So they wanted to explore HTL code generation from MATLAB, and it required them to rewrite their MATLAB to be hardware ready and to adopt Simulink for the high level design. They put much of their MATLAB into system objects, and then they generated HTL code. So they used co-simulation, hardware co-simulation, to verify that the HTL behaved like the algorithm. To test it with their original algorithm, and overall the generated HTL produced a much more resource efficient prototype much sooner. So they reduced the time to generate code and reduce the time to manually handwritten the code. Then they explored using the code for production of ASIC implementation. With a little optimization work, they were able to get the area to be less than the handwritten handwritten RTL code, and the negative slack, which was nearly meeting their timing. But they still want to explore more to optimize that one. And overall, being able to generate HDL automatically without writing it manually and investing time to write manually the HDL code, and verify it much sooner in order to get onto a FPGA prototype, saved them a lot of time and on their schedule. So they will be able to deliver the product on time. So the good thing with the HTL coder tool is it provides the flexibility in design and simulation environment. So I mean by flexibility is that you don't need to build up the whole algorithm or whole model from scratch. You can directly use some domain specific libraries which are supported for HTL. Like you can use signal processing. If any signal processing application, we have DSP HTL toolbox. For any wireless communication applications, we have wireless HTL toolbox, and for vision, we have vision HTL toolboxes for vision applications. You can reuse the IP by co-simulating the handwritten HTL code, like I earlier said, using HTL simulator, which are provided by Mentor Graphics, like QuestaSim or Cadence, like Minsys. So you design and simulate your algorithm in MATLAB or Simulink environment. You can reuse your IP, and you can use specific libraries to support the HTL part. So we see that customer really achieve good benefit by breaking the wall between these different roles and allow them to collaborate in one environment. So to start off with the generating verification component to increase the productivity of verification. Then co-simulation helps them to get together and debugging and solve the issues faced earlier. And then doing more verification by providing the implementation details and refining the model, help them to reduce the efforts for respinning the whole design after finding a bug later. And then finally refining the design by finally generating the error-free synthesizable code helps reducing them to eliminate more design errors. So this thing we saw in the survey part, that the main root causes for functional flaws are because of the design error, changes to specification incorrect or incomplete. So this workflow, the whole workflow eliminates a lot of design errors and specification related errors, which can help customers to achieve big benefits. To start with the tool, you can go through some on-ramps which are available on MathWorks website. We share the link along with the presentations. And to gain the tool experience further, you can go with the trainings available in MATLAB and on MATLAB and Simulink training. So there are some wireless communication systems with even USRP, software-defined radios, some LTE to 5G trainings as well, for HTL code trainings as well. So the links are provided in the chat as well. And if you want to have some customized training courses, you can contact to the training team as well for gaining more for the expertise in the tools. This is it from my side. For any queries, I'm open to, like, this is my email ID, niharika@mathworks.com. You can contact later also for any queries related. Thanks, Prashant. That's it from my side.
Yeah, thank you, Niharika, for your insightful presentation. And we now open for Q&A. So please feel free to drop in your questions in the Q&A section, and we'll have them answered for you.
Prashant, if there's no question, I can go, like, whenever we deal with the customers for HTL verifier, we have some commonly, like, we do, like, we face some commonly asked questions. I can go with them.
Yes, yes, we
Yeah,
have time.
yes. So the first question we most commonly get is that, do we support Xilinx Vivado for co-simulation as well? To answer that question, currently we support complete automated HTL co-simulation setup for Mentor Graphics and Model Sim or QuestSim and Cadence. But as mentioned, we currently do not support the Vivado, but we, in this area, there's a continuous focus of MathWorks, and you'll be able to see soon that we will support the Xilinx Vivado as well for co-simulation. the next common question which we have, we generally asked by customers is that can we like, do we also support the pre-handwritten RTL code as well for co-simulation, or yes, we support the pre-existing HTML code by using Cosin Wizard. It's a app, or you can say it's a GUI for the co-simulation part, where you can import your VHDL code directly, and then you can apply all the constraints, or you can apply the clock frequency and everything, and then you can generate a co-simulation model with that, and it will generate you the it will, and you can verify your design with that co-simulation model. The one more, I'll go for the last question, is like, does the like basically does what are the interfaces which we support in, like, between PC and board for the FPGA and loop? Like, we've seen that there were different workflow, there were different verification methods, which includes FPGA and loop as well. So currently, we support JTAG, Ethernet, and PCI Express interface, and JTAG being the slowest and PCI being the fastest interface for supporting the FIL. So that's it from my side, Prashant. Thank you. I hope this helped all of you to gain some knowledge about the HTML verifier.
Yes. Thank you, Niharika, for bringing that up. Dear audience, again, if you have any questions, you can type in the section, or please feel free to write to our team. Here are the email IDs. You can make a note of it. So please, if you have any questions, please write into us and we'll get them answered for you. Also, we will be sharing the recordings and the presentation copies of all the 3 sessions in this series. So if you have registered, you will get it in your email ID. And I would also like to say thank you to all our speakers for all the 3 sessions, for sharing your insightful presentations. And also thank you, audience, for staying throughout the session. We look forward to meeting you all again. Thank you. Have a good evening.